Imagine a world where your network router is powered by an artificial intelligence model. It sounds like science fiction, but the idea of an LLM acting as a user space IP stack has sparked serious debate. The question on everyone's mind is simple: how fast does Claude respond to a ping? The answer reveals a fundamental flaw in this architectural approach. We are not just talking about speed, we are talking about the very definition of reliability in networking. By the end of this video, you will understand why treating a probabilistic model as a deterministic protocol is a category error that breaks the internet. To understand the stakes, we first need to clarify what a ping actually is in the world of computer networking. A ping is an ICMP echo request. It is a tiny packet of data sent across a network to measure the round-trip time. It requires immediate atomic action. When a packet arrives, the system must process it and send a reply within microseconds. This is the heartbeat of network diagnostics. Now consider the architecture of a large language model like Claude. It is an inference engine designed to generate text token by token. It relies on attention mechanisms and sampling strategies that introduce inherent randomness. The time it takes to generate a single response can vary based on the context window, the complexity of the query, and the current load on the inference server. This variance is known as jitter. In a deterministic system, jitter is a bug. In a probabilistic system, jitter is a feature. Here is the thing that changes everything. A network protocol stack requires strict, bounded timing guarantees. When a TCP handshake begins, every millisecond counts. If a packet is lost, the system must retransmit it within a specific timeout window. If the response to a ping takes 2 seconds, the network stack will assume the packet was lost and initiate a retransmission. This creates a cascade of errors. The system becomes flooded with duplicate packets. The connection degrades into chaos. The model is not failing because it is slow. It is failing because it is non-deterministic. The latency is not just high, it is unpredictable. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Let us look deeper into the mechanics of why this fails. When an LLM processes a request, it does not execute a function call. It predicts the next token in a sequence. This process is sequential and serial. To generate a response that looks like a network packet, the model must first parse the input, then reason through the logic, and finally generate the output character by character. This entire pipeline happens in user space, far removed from the kernel where network drivers operate. The overhead of serializing the input, sending it to the model, waiting for inference, and deserializing the output creates a latency gap that is impossible to bridge. We're talking about a performance difference of several orders of magnitude. Kernel-level implementations operate in microseconds. LLM inference operates in seconds. That is 1,000 to 10,000 times slower. This brings us to the concept of atomicity. In networking, an operation is atomic if it happens all at once or not at all. There is no middle ground. If you send a ping, you get a complete reply. If you do not, you get nothing. An LLM cannot guarantee this. If the generation process is interrupted, or if the model hallucinates a control character, the output can be truncated or corrupted. You might receive half a packet. You might receive a response that looks valid but contains invalid checksums. This creates a reliability failure mode that is unacceptable for any critical path networking. The system cannot distinguish between a slow response and a corrupted one. It simply sees a failure. Now consider the implications for system design. Developers often try to solve these latency issues with application layer workarounds. They implement watchdogs that monitor the connection and send periodic pings to keep the session alive. They add timeout logic to handle the long delays. These are not fixes. They are band-aids on a broken foundation. These mechanisms prove that the LLM cannot natively sustain the continuous, low-latency state required for a functional network stack. The system is fundamentally decoupled from the hardware state. Network availability becomes tied to the health of the model service rather than the physical network. If the model service hangs, the entire network stack dies. There is no fallback. There is no redundancy. The core insight here is that you cannot build a deterministic system on a probabilistic foundation. The architecture itself is flawed. It assumes that the output of an LLM can be treated as a binary signal, but it is not. It is a statistical prediction. When you try to force it into a role that requires absolute certainty, you create a single point of failure that scales poorly. The moment you need to handle high throughput, the latency variance becomes unmanageable. The system collapses under its own weight. This is not a problem of optimization. It is a problem of first principles. We must also address the confusion around terminology. In the Anthropic ecosystem, the term ping is often used to describe application layer health checks or cache refresh mechanisms. These are software operations that happen at the API level. They are designed to prevent prompt expiration or detect SDK hangs. The latency metrics for these operations are measured in seconds, not microseconds. This is a completely different domain. It is about application logic, not network protocol. When people discuss pinging Claude, they are usually discussing API latency, not network stack performance. This distinction is crucial. It means that the premise of using an LLM as a user space IP stack is based on a misunderstanding of what an LLM actually does. It is an inference engine, not a network driver. The lack of benchmark data on this topic is telling. There are no practitioners reporting successful deployments of LLM-based IP stacks in production environments. This is because the failure mode is too severe to ignore. The trade-offs are simply too steep. The flexibility of an LLM comes at the cost of determinism. The speed of a kernel comes at the cost of flexibility. You cannot have both. If you need a network stack, you use a kernel. If you need an LLM, you use a model. Mixing the two creates a system that is too slow to be useful and too unreliable to be safe. The lesson for any engineer building systems with AI is to respect the boundaries of the technology. Do not try to force a probabilistic tool into a deterministic role. Understand the fundamental differences in how they process information. An LLM is a powerful tool for reasoning and generation, but it is not a substitute for the underlying infrastructure that makes the internet work. Recognizing this limitation is the first step toward building robust, scalable systems. It is about knowing when to use the right tool for the job and when to avoid the temptation of a shiny new approach that looks good on paper but fails in practice. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.